Okay, welcome back, Astronomy 1010. Today is lecture 10. We're going to continue lecturing about terrestrial planet geology, learn about the interiors of planets a little more, and eventually how that manifests itself as geology at the surface of the planet. Then we're going to do a lab on the relative ages of Martian landscapes. We're basically going to explore the surface of Mars using the legendary Mars MOLA topography map, where we'll look at the dead volcanoes on Mars and all kinds of other interesting things. A reminder to the class that you may not need to actually print out the lab for today, because let me share my screen to show you the concept here. I'm thinking when we do our lab today, you will need the Mars topographical map. Okay, so I just opened that up. And you will also need the landscape of Mars handout. And today's lab is sort of an exploration of Mars, where we're going to sort of be asked a bunch of questions to probe our understanding of planetary geology. Since most of our answers are going to be in the form of 1 or 2 word short sentences, I'm going to actually just use the editor here. Let's see, I might have to open up, I don't know if I can do it on the web-based one, but if I open this in Acrobat, I should be able to make some markings right onto the page. I think if you use this tool, not signature, oh yeah, here, this one here. I'd love to change that font choice, but I can put my name, sorry. So you'll be able to do that kind of a thing right on your sheet there, okay? I think you can even, oh, I thought we could move it around afterwards. Anyways, that's for lab time, but I thought I'd let you know. This is the topographical map. You'll definitely want to print that out to your computer, and we'll look along there together. Okay, so that's just a heads up on what to expect come lab time. Other comments and questions? I graded a bunch of papers yesterday. I closed out some homeworks. You guys need to get better at making sure you're turning in your labs and your homeworks that week, because I'm grading them and I'm closing it out. And sometimes I can even see people who should have been there not turning stuff in, and that's very disturbing to me. It's going to be really disturbing to you when you realize how bad it hurts your grades. So you guys have to keep up with the work here, right? That's the madness that we all signed up for. You pay me to torture you, and I torture you, and then you torture me, and we're torturing each other. And that's what a class is, okay? So you've got to show up for the torture, otherwise nothing happens, all right? Enrique is going to think about that one. Okay, anyways, let's get to it. Let's see where we left off last time. When we talk about planetary geology, we have to first talk about the interior heats of planets. And the interior heat of planets is different than the surface temperature of planets. Do any of y'all remember why? I'd like to start the day by asking you guys what the hell you learned last time. What does this picture tell us about the interior heat of terrestrial planets and how they compare to one another? Okay, we could try this slower and easier. Wait, am I recording? Does it say record at the top of the page there? I think I'm recording. Yes. Okay, you guys need to talk to me today. Yes, Cam, thank you. All right. You must talk to me. All right. Let's try a simpler question. What the hell is a lithosphere? Who knows what a planetary lithosphere is?
Is it the crust?
It's kind of like the crust, but it's different than the crust. How is it different than the crust? For instance, I can see here Mathis?
Yeah, Matt is fine.
Matt, okay, thank you. Matt, I can see here that the crust of Mars is this little tan yellow stuff, but the lithosphere of Mars goes down to there. So clearly on Mars, the crust is not the lithosphere. Clearly on Mercury, the crust is not the lithosphere, and certainly not on the moon is the crust the lithosphere. Maybe you need to flip open your notes one page back and read
I
the.
found it.
All right, Andrew, regurgitate.
All right, so it's a hard, brittle, frozen outer layer of a planet.
And how would that differ than the crust?
Because the crust is inside and it'd be soft.
No. The crust is on the outside. This is the crust of Earth. This is
All
the
right.
crust of Venus. This is the crust of Mars.
Mhm.
How does a lithosphere differ than a crust, from a crust? The crust is layering by density, not by strength. Lithosphere equals strength. Crust equals density. This means that Mars's lowest density layer is out here. And by the time we get to the red stuff, the density has increased with more metallic elements. And yet it's still frozen solid. There's no convective bubbles bubbling around inside of the mantle of Mars. There are convective bubbles bubbling around inside of Earth and presumably on Venus as well. Okay? The lithosphere is a measure of how frozen the outer layers of a planet are. Okay, let's try another question. What's the difference between internal heat and surface temperature? What causes the surface of a planet to get hot?
Its distance from the sun.
Pretty much. Good job, Frank. The distance from the sun. So and it also depends upon atmospheres a little bit, but let's just take a weirdo like Mercury for a second, right? Here's a nice picture that I was just thinking of, so I'll share it with you. Mercury has two wildly different temperatures. The daytime temperature on the subsolar side, subsolar means you're the point underneath the sun, can be upwards of 700 Kelvin. That's kind of hot. The nighttime side of Mercury, where there's no sunlight, is 100 Kelvin. That's just 100 Kelvin above absolute zero and well below the freezing point of water. Actually, it's close to the freezing point of nitrogen, I think. So sunlight is what makes the surface of a planet hot. But mostly sunlight makes the surface of a planet hot, and then the planets tend to re-radiate as black bodies and shine the light right back off into space. That's not what makes the interior of a planet hot. What makes the interior of a planet hot?
Would it be the size of it?
In a way, yeah. The size causes some other things to happen. Let's review them as well, okay?
It could be like a few different things, right?
Yeah, it depends on what.
Accretion.
Exactly. Thank you. That was Jake there. Jake. These three things play a different role depending on what point in the planet's history you're thinking about, right? So when the planet first forms, accretion brings all that matter together. Actually, can you guys pause for a second? Hey, Jordan, would you turn the temperature down to 68? Because I'm starting to have a little overheating, a little excess interior heat myself. Thank you kindly. Okay. So first, a planet forms. And when a planet forms, all of the disk of rocky material starts to collapse into a warm, molten ball. I bet you when the Earth first formed, let's type in, we have to talk about this today anyways, the heavy bombardment period. There's a nice little Wikipedia image. And this is some space art. Obviously, nobody's GoPro camera was sitting around 4.6 billion years ago to watch the Earth form. So we have to use what we know about physics and computer modeling to tell us that. And then we ask our weed-smoking artist friends to draw us a picture. This is probably what the Earth looked like shortly after formation. It was probably so warm that it was molten rock at the surface and it was glowing red, and all of the bits of material that just clumped together made it extremely hot. And as it cooled off, it probably started to resemble something like the moon, except with volcanoes. If there are any Star Trek fans out there, it probably looks like the planet Vulcan, which is a planet full of volcanic activity or something like that, okay? Now, after a while, the planet will start to cool, but then there are secondary and tertiary processes that keep a planet warm. Oops, sorry. People make a big deal about the differentiated layers of Earth. And what that statement means, differentiated layers, it means that Earth is segregated into a low density crust, a medium density mantle, and a high density metallic core. When Earth first formed, this Tootsie Roll layer was probably not present. Probably there was a homogeneous mixture of all these materials. What happens is over time, the heavy metallic elements, which have higher density, will sink down towards the bottom. The lighter material silicate rock will buoy up to the top. This is like styrofoam in water. This is like a stone in water. The heavy metals sink, the light rocks rise, and as they move past one another, they generate friction, which continues to heat the planet. Today, our planet is pretty well differentiated with a crust mantle core, but some of this is probably still happening. The convection that takes place on Earth is probably still continuing to differentiate Earth's layers. The third process is radioactive decay. There are radioactive isotopes buried in the ground rock beneath your feet and all around you. You know, you smoke the equivalent of 1 to 2 Marlboro cigarettes per year, whether you like it or not, just from radioactivity in the ground rock around you. Some of it takes the form of radon. That's why you have to check your houses for radon before you purchase one. Hell, I can measure some of this radioactivity with my boy here, with this Geiger counter. I even have some radioactive test samples, okay? So let's get freaky. Let's hunt for radioactivity in our daily lives. Now, do you guys know what the 3 forms of radiation are discovered by Madame Curie? Do you remember what those forms of radiation are? I taught them to you at one point, I hope. What are the names
Is
of
one of them toxic?
Well, they're all toxic. Ain't none of them good for you, son. Hold on, I'm having trouble. Here we go. Okay. Madame Curie discovered 3 types of radiation through her investigations of radium, for which she won the Nobel Prize and eventually died of cancer. Madame Curie discovered the 3 types of particle radiation. This is something you should kind of know about as a scientifically educated person. She thought they were new types of electromagnetic waves. She thought she was discovering like another type of radio waves or something. Little did she know she was measuring particles coming off of substances. She discovered alpha rays, beta rays, and gamma rays. These so-called alpha particles ended up being the nucleus of a helium atom. 2 protons and 2 neutrons. So just a broken off helium nucleus. The beta particle ended up being just a free electron. And in a weird twist, the gamma rays ended up being a new type of electromagnetic radiation, a very short wavelength, high energy photon. I believe these Geiger counters can measure at least alpha and beta particles and maybe even gamma rays. And they're all around you. During the course of my lecture, some of these particles will strike your forehead and create little mini nuclear explosions on your face. You probably won't notice it, but if there was enough of them going off, they'd probably give you cancer eventually. Let's see here. Can you guys hear the click? Oh, don't tell me. Here we go. So this is measuring, if you can see here, wait, that's too shiny. This is measuring millirads, wait, is it millirads? Yeah, millirads per hour, okay? And listen for the clicks as I hold my wand around. Can you hear those clicks?
Yeah.
Those are alpha particles and beta particles striking my wand. They're just coming from around the room. Ooh, I just got a little spike there. Okay, we can now we can calibrate this with some test cycles. Okay, so let's try, what do we got here? We got some good stuff. We got polonium-210. That's what they killed that Russian secret agent with in England, polonium-210. We got strontium-90. We got cobalt-60. Okay, I probably shouldn't even be touching those, but okay, so let's listen for the clicks. Let's see if I have enough hands to do this. Okay. So first I'm going to go to polonium-210. A little extra clicks, but polonium-210 has a very short half-life. Now I'll go to strontium-90. Ooh. Now we'll go to cobalt-60. Whoo, doggy! That puppy's a little bit hot. Okay, now listen. When I went to undergraduate school in Tucson, Arizona, I had a friend, a science friend, who went out to the Tanque Verde swap meet. It's a sort of, it's a swap meet is like a thrift store in the middle of the desert, and it's run by weirdos. And you can buy everything from AK-47 to chopped off deer hoofs laying on a table. It's a wild west out there of crazy stuff you can buy. He brought me a present back. I want to share it with you. He got me my very own rock of carnotite. Carnotite is a uranium ore, okay? Look at this shit. That, my friends, that's pretty much straight up yellow cake. Do you see that yellow rock? That's basically, look, you can see it's sort of frosted on the tips there, like it was some sort of frosted flakes. This yellow stuff you see, that's what they make. Well, I don't know if they make it from carnotite, but that's basically yellow cake. That's what they take uranium and enrich it from. This will be a mixture of uranium-238 and 235. Now, I was told the sample wasn't that radioactive. Let's find out. Here we go. Okay, so they told me, don't worry, the plastic box will shield most of the alpha particle radiation. You know, the plastic box will really shield this thing. And then I was like, okay, we better get a lead box for this thing. I didn't realize there was a difference between lead and lead foil, so I got a lead foil box. Okay, let's see here. Here's my. I guess that's not doing too much. So we're just going to go and tuck this back behind the steel I-beam in the corner of my room, okay? Now look, you too can own your very own your own rock of uranium. If you just go out and dig amongst the treasures of planet Earth, you might be able to find some radioactive materials out there as well. You can irradiate your friends and your office mate and all kinds of other people who will be greatly upset at you. Okay. Could you imagine? And think about it, friends. We're just kind of digging around in the crust of Earth. The people who find these samples, they're just scraping that little bit off the top, right? What if you could dig all the way through the Earth? Imagine how many lumps of radioactive materials would be present. In our homeworks this week, the book estimates that the interior of the Earth generates 30 trillion watts of power just from scattered radioactive isotopes contributing to the interior warming of Earth. Do you think it would be better to be a big planet or a small planet if you want to keep your interior hot?
Would it be a smaller planet because it's so compact?
We will find out, Frank. I wanted you to take a guess, and then we'll test your guess against what the experts say. The first
Okay.
question is, Frank, planets start off hot, and they have ways like radioactivity and differentiation to keep them hot. But obviously, planets cool down over time. And so we have to ask ourselves, how do planets cool? They cool because they basically shine light into space. Now, remember, there are three modes of energy transport in nature, okay? There is convection, where hot bubbles of rock rise and cold bubbles sink. Convection is how energy is transported through the Earth's mantle. Then there's conduction. Conduction is direct contact, atom to atom jiggling. And conduction is how energy is transported across the Earth's lithosphere, which is a solid layer. But eventually, once you get to the top of a planet, even just ignoring the atmosphere, the planet is touching the vacuum of space. You cannot transfer energy into space by conduction or convection. Is that obvious to you guys why, or do I need to explain that? Can anyone out there explain why convection and conduction cannot transmit energy into outer space?
Space is cold.
False. Space does not have a temperature. All right, there's the cosmic microwave background, but I ain't talking about that right now. You're not ready for that. Space is a vacuum. What is the definition of temperature? I thought you guys knew the definition of temperature.
Well,
Why is my coffee hot?
oh, conduction.
No. What does the temperature mean? What is temperature a definition of? I'm sorry, let me say that better. What does temperature measure? What physical property?
Oh, average kinetic energy of a system of particles, gas, liquid, solid,
Beautiful.
matter.
So Andrew, if the vacuum of space is a effing vacuum, there are no particles there. If there are no particles, there is no temperature. The particles neither move fast nor slow because there are no particles. You can't transmit heat to space. By the way, that's why your thermos has a fucking vacuum in it, right? The vacuum is designed to prevent energy being transported through convection or more likely conduction. The only way you can get energy into outer space is through radiation, by shining. You got to shine your energy into space. Why don't we do a little problem on that so you can imagine how Earth cools down, okay? Let's imagine Earth as a hot rock in space. And let's write this note down. Planets cool via radiation. And I'm not talking particle radiation like I just irradiated myself with. I'm talking about electromagnetic radiation. Here's Earth. Earth is a sphere, and it is a warm sphere. And warm spheres that are dense act like black bodies. If you have a temperature, then you glow because you are hot, okay? So here's Earth shining into space. The average temperature of Earth is 15 degrees Celsius. Does anyone know what that is in Kelvin? How do you convert from Kelvin to Celsius? Jeez. Okay, so absolute zero is minus 273 Kelvin. After that, sorry, no, oh, sorry, not geez, let me try that again. Is minus 273 degrees Celsius. And we set that equal to 0 Kelvin. So you just add 273 to Celsius, And that gives you 283, 288 Kelvin. Okay. We want to ask two questions. How much light does Earth give off? And what's the peak wavelength? So let's try to do those questions here. So question one will be, how much light does Earth emit? How many watts per square meter? And we'll answer that question with the Stefan-Boltzmann law. These are the kind of things I'll make you do during the final exam, okay? So pay close attention to what's happening here. It's going to be in your future. Sigma is the Stefan-Boltzmann constant. The brightness is 6 times 10 to the negative 8 watts per meter squared per Kelvin to the 4th times the temperature in Kelvin, 288 Kelvin, raised to the power 4. Okay, class, go. Calculate the brightness at which Earth radiates. You all know how to take a 4th power, right? Does anyone have an answer? Guys, what's going on? You're scaring the willies out of me here. I got to go into gallery view so I can see all of your shame. Who knows how to do this? Yes, Cam. Cam's got it. Enrique, did you get it? Jake? Look. Cam got it. You just do 6 exp minus 8. You watching now? Because if you can't do this, you got to watch me. Times 288 to the power of 4 equals. What's my final answer? 2 sig figs. Come on, guys, just give me a number.
I'm going to say 413, 430
That's 3
Kelvin.
sig figs, Andrew.
Oh,
Would it be 41 Kelvin?
Wait, rounding
Oh,
does
wait.
not mean you change the order of magnitude. This is a number of order 400. You can't make it anything other than 400. I want 2 sig figs, though. Jesus, guys, you're making me want to drink, okay? And I already want to drink. It's 400. All right, we got to have a talk. If you have a number that looks like this, and I say please round to 2 sig figs, that does not mean, Frank, that you change 400 to 40. That is called molestation of numbers. You are not allowed to be a molester of numbers, okay? This is a number of order 400. It will stay of order 400. 2 sig figs mean you keep the 4, you keep the 1, and everything else turns into a 0. Okay? 410, what are the units?
Kelvin.
Nope. Kelvin to the 4th cancels with Kelvin to the 4th.
Oh, yeah.
Watts per meter square.
Watts per meter squared. Thank you, Bella. Someone's with me. 1 square meter of Earth's surface, a panel about the size of this board here, gives off about as much energy, 400 watts, as a commercial house spotlight, okay? But Earth does not glow at visible wavelengths. If we want to ask the next question is find the peak wavelength emitted by Earth. We would have to use Wien's law, which tells us that the maximum wavelength of emission is given by 3 million nanometer kelvins divided by the temperature. Okay, guys, plug in 288 and tell me what you get. And once again, please round to 2 sig figs. Frank, why don't you round to 2 sig figs? That should take you all of 1.2 seconds to calculate. Frank?
Almost all set.
Guys, it's 4 buttons. Just push them. 3 exp6 divide by 288 equals. Jesus, this is not hard. I'm feeling frustrated here today.
It would be 10,000.
Stop. That's 2 sig figs. 10,400 rounds to 10,000. What are the units?
Nanometers.
That's right. In what regime of the electromagnetic spectrum is 10,000 nanometer light? Better use a cheat sheet.
Is it infrared?
Yeah. How'd you know that? Jake, you good. How'd you know that?
I was trying to remember. I think infrared was on like the higher end, like
Above
bigger
visible.
numbers.
Well, after red comes infrared, right? Let's see how good you really are. How many microns is that? 10,000 nanometers is how many micrometers? Micro is 10 to the minus 6, nano is 10 to the minus 9.
100.
Nope, try again. 1,000 nanometers is 1 micrometer.
Oh, is it 0.01?
No. It's 10 micrometers. A nanometer is a billionth of a meter. A micrometer is a millionth of a meter. They differ by 10 to the power of 3. That's 10 microns. 10 microns is pretty close to the wavelength at which you radiate as a warm glowing object. You know, like if you're in the military, those night vision goggles, how Al-Qaeda looks like a little red glowing blob? That's because Al-Qaeda gives off infrared light, and so does your dog Spot, and so does planet Earth. They are hot, dense solids that are close to 300 Kelvin. They glow around 10 microns. This is how Earth cools over time. This is how all the terrestrial planets cool. They shine their energy into space. So Earth is shining away infrared light. And it's shining about 400 watts for every square meter of surface. I'd like to note to you guys that is exactly roughly the same as the amount of energy that we get from the sun. The surface of a planet is controlled by, so the surface temperature of a planet is controlled by sunlight, which is then re-radiated back into space. Now, Earth gives us about 400 watts per square meter. There's a little bit extra from geothermal energy, but that's a story for our homeworks this week. I need to erase here. Any objections? Okay. Let's answer the question, who stays hotter longer, bigger or smaller planets? The answer to this question has to do with something that the book calls, well, the book calls it the surface area to volume ratio, but I'm doing it a different way. I'm going to call it the volume to surface area ratio of a planet. It's kind of a big concept in planetary science. Let's take a planet and let's imagine it's a sphere. The sphere has radius r. Now, the volume of a sphere is equal to 4/3 pi r cubed. And I'm going to go ahead and go out on a limb and say the volume of a planet will be proportional to the amount of accretion it has. Bigger planets have more accretion. Bigger planets have more differentiation. And bigger planets have more radioactive decay. So the volume of a planet is proportional to the amount of internal heat that you get, because you have more radioactive materials, you have more material forming the initial snowball of a planet. On the other hand, the surface area of a planet goes as 4 pi r squared. And obviously, guys, if you have a bigger surface area on a planet, you're going to have more square meters with which to radiate away light. Earth can shine more light than Mercury because it has more panels at its surface. So the surface area is proportional to the amount of cooling, or the cooling rate. Therefore, if we take the ratio, the volume to surface area ratio, it'll tell us how much more heating, internal heat you get versus the cooling rate. Because see, at first it looks like a bigger planet will cool more, and at first it looks like a bigger planet will hold more heat. But once we take the ratio, we discover something. Can you guys see which terms will cancel if I divide these by each other? Which terms will cancel?
You can take pi r squared away and you would just be left with pi r.
What about 4? We could take away the 4 too.
True.
Wait, if you take pi away, there is no more pi. So what's left?
Oh, yeah. R cubed.
No. R
Oh, just r, just r.
But what about the 3?
3r.
The 3 is on the bottom, dude. 1/3 r.
Bad at math, Brendan.
Okay, well, we're trying to get better, right? We're growing. We're growing. The way you get better is by screwing up, and then I slap your hand, and then you learn something, okay? Pain brings up questions about origin. 1/3 r means something. It means that the volume to surface area ratio is proportional to the radius, and this is proportional basically to the amount to the heat holding capacity of a planet. In other words, let's spell out what this means. This is the point. As the radius of a planet grows, the heat holding capacity grows. So unlike, unfortunately, what Frank said, bigger planets stay hotter longer. What does that have to do with my picture of the lithospheres of planets? Let's go back to that slideshow here. Can you tell me what that thing we just did has to do with this? The thing we just calculated there is related to the lithospheres in these pictures here. What's my point?
Didn't you say the thinner the lithosphere, the more heat it has?
Yes, Enrique, this is the point I'm trying to make. Okay, so let's now follow up with that, Enrique, and say, according to this picture, which planets seem to have the thinnest lithospheres? This is your lithosphere here. That's your depth of lithosphere.
Bigger planets have thinner lithospheres.
In other words, these planets have a lot of internal heat, right? What about the little guys? Mercury's kind of weird, but Mars and the moon and Mercury are kind of frozen out. They're frozen dead because these guys probably radiated away their internal heat so quickly that their lithosphere just froze out. These are frozen chicken McNuggets. These are warm apple pies. I don't know what Thanksgiving analogy you want. Maybe you're going to be eating chicken nuggets this year. I don't know. But look at the bigger planets are still warm, and that's why their lithospheres are thin. You want to know why that matters? Because it turns out that if your planet is warm on the inside, that warmth comes bubbling out through the lithosphere and eventually takes the form of crazy geology. Remember that earthquake we had last week? That earthquake is a manifestation of the interior heat of Earth trying to break through our thin lithosphere. Let's add that to our notes, thus we don't forget. More internal heat equals more active geology. Planetary scientists use the lithospheric depth as a measure of how geologically active a planet is. But you have to go through all of these logical steps to understand that. Okay. What have I done so far? I've explained to you that internal heat is associated with bigger planets, and bigger planets are more geologically active than smaller planets. Now we have a remaining job to do with the rest of our day today. What form does that geology take? And now I want to get on to a very big subject called the 4 geological processes, okay? So let's zip ahead in our slideshow, see if I can find the picture here. Once the internal heat starts bubbling through the lithosphere, it can take a lot of different forms. But in our class, we're going to classify geology into 4 broad categories. 4 things that we're going to look for as we poke around the surfaces of Mars today. The 4 geological processes are the sculptors that shape a planetary surface. Sorry, I'm trying to just get to my board here. I'm going to erase this nonsense. Now, some of you may have taken a geology course here at CCRI. The geologists like Emily and Paul and Matthew are in my department, and they've taught me a lot about geology over the years. I'm more of an astronomer type. But astronomy and geology come together in planetary science. Planetary science is geology for other planets, but it also forces you to kind of look back at your own planet and think about what's cool about it. The 4 geological processes I want you guys to think of them as like sculptors. They are the sculptors that shape a planetary surface, all right? They're what makes Pluto look the way it does. They're what makes Earth look the way it does with its continents, or Mars look the way it does. And they can be broken down into one of four categories. Impact cratering, volcanism, plate tectonics, and lastly, erosion. Almost every type of geology can be sort of placed into one of these categories. What about the earthquake that we just had last week? That magnitude 4 earthquake, which of these categories would we place it in?
Plate tectonics.
Okay, cool. I figured you guys knew that, but I wanted to test you. Nice. I want to talk about these each in turn, but I tend to spend a lot of time in impact cratering because it's kind of fun. So let's begin there. Impact cratering takes place because there are lots of rocks flying through space that from time to time crash into the surfaces of the planets. So let's just get a couple of terms straight off the bat. There are meteoroids. There are meteors. And there are meteorites. I'm guessing you guys don't know the difference between these, or are there any rock enthusiasts out there that do? A meteoroid is a rock when it is in space. When the meteoroid hits the atmosphere, it becomes a meteor. So that's when it's in the sky, okay? And then a meteorite is once it's on the ground. For instance, I have a big old lump here. Hey now. Oh, here it is. See this? See this iron meteorite here? This was once a part of a much larger meteoroid, which flew through the solar system for billions of years. And one day, 65 or maybe 80 million years ago, struck Arizona, a location called Meteor Crater, and fragmented into bits, and then left one of these bits behind. This is a meteorite. I wish I could pass it around to you guys like a show and tell. It's very heavy, much heavier than a block of granite. That's because it's made mostly of iron. It's an iron meteorite. And you know, it is a real treat to see the impact craters that they form. Usually what happens is you have your meteoroid flying through space. It's some kind of a large, it's not always spherical, it's just some potato-shaped chunk of an asteroid. It flies down and it strikes the ground, and it has so much kinetic energy. It has a lot of mass and a lot of velocity, so much kinetic energy that it basically strikes the surface of a planet like a little nuclear missile. And it excavates a crater. Let's diagram out our crater here. You smash and vaporize a bit of rock, and you eject a bunch of material out of the crater. Basically, some of the rock just gets vaporized into gas. You form a crater rim. That's the rim of the crater. Sometimes you guys remember there'll be a peak. This is called the basin. The bowl of the crater is called the basin. You'll have a peak, and then you get rays of ejected material. That's a little diagram of a crater there. Rim, peak, basin, ejecta. They sometimes call them rays. I was lucky enough that when I went to school as an undergraduate in Arizona, and during my spring break sophomore year, my father and I took a trip to explore Arizona, and one of the places we went to is this legendary impact site called Meteor Crater. It's out in the eastern Badlands of Arizona, and you have to drive for hours to get to this thing. It's pretty wild. Let's see if we can find a nice high resolution picture of this to share with the class. It's kind of funny, the impact crater itself is on private property. It's actually on a dude ranch. They call it the Barringer Meteor Crater. So when you drive up to the site, you have to like park in a parking lot, and you have to pay $20 to see the crater. And they make you walk through this gift shop with I love alien UFO keychains and things. It's total Arizona weirdness. And then you get to stand at the edge of this thing and look out over this impact crater. It's about a mile in diameter. It's epic. The size of the rock that made it was not the same size as the basin. It's much smaller. But I believe like a meteoroid will excavate a basin that's anywhere from 10 to 100 times greater than the diameter of the meteoroid, if you assume a traditional speed of a meteor through space, or a meteoroid through space. If you stand here and look at this thing, you think, wow, this is a hell of a thing. I'm sure glad I wasn't here when this thing struck, because that would have been particularly violent, right? But seeing something like this on planet Earth is actually quite extraordinary and rare. There's a reason they get to charge you $20 and you will pay it to see this thing, is because you won't see this in Rhode Island and you won't see this just anywhere. You've got to go to special places. In fact, let me show you another famous meteor site, crater site on Earth. It's called the Wolf Creek Crater, and it's located in Australia. And I want to show you a picture of Wolf Creek Crater, and I want you to compare it to Meteor Crater and ask yourself what's different. So let's get a better picture of the meteor crater from space. Here's a good picture. This is a nice aerial shot of meteor crater here, okay? So you can really see the interior of the basin. And let's see if we can get a nice aerial shot of Wolf Creek Crater. Images. Yeah. That's a nice, juicy picture there. Okay, so here's a picture of Wolf Creek Crater, and here's a picture of Meteor Crater. Now, you guys aren't necessarily trained in impact cratering yet, and that's kind of the fun of it. I want to know, what are you thinking here? Like, if you look at this crater versus this crater, what are the differences?
Wolf Creek Crater looks like a flat bottom.
It does kind of look like a flat bottom, yeah. That's a good point, Jake, and I like how you're using some of the stuff you learned during our lab last week. Suppose you had to take a guess about which one was older. What do you think is the older crater, Meteor Crater or Wolf Creek Crater?
Wolf Creek.
Everyone kind of knows that. And how do you know that? How do you know that's the older one? That's good.
It looks like there's like some new growth inside of it.
Yeah, well, you know, this
There's
probably
more
fills
like
up with you're in the desert here, so if this fills up with a bit of water, there'll be a little more vegetation there. But forget about the vegetation for a second. Just talk about the basin and talk about the rim. How are the basins and the rims different for Wolf Creek versus Meteor Crater?
More shallow.
Yeah, Wolf Creek is kind of shallow, filled in. What process might be causing that?
Erosion.
Yes. And this, my friends, is why you don't see the craters on Earth that you do see on the moon. See, it's rare to see something like this because a crater might happen once every 100 million years. But how long do you think it takes to fill in and wear a crater down through erosion? Probably takes 100 years at best. Or, well, okay, maybe 1,000 years. But 1,000 is a crap load less time than 100 million years, right? Earth has a dynamic set of planetary geology. It has a lot of erosion and plate tectonics and volcanism. And if Meteor Crater one day is going to look like Wolf Creek Crater, The rim will get chipped away by sandblasting and rainstorms. This will get filled in with sediment. Eventually, it'll completely disappear. You know what it might look like many, many years from now? Let me show you another crater site on Earth that really tells the whole story. It's called the Manicouagan. Okay. I can't spell this. Yeah. Manicouagan crater, which is in Ontario. You can only see it basically from outer space. And it's not even a crater anymore. It's like a river. That was once a massive impact site. And over the years, it basically just got worn down to the point where the rim just eroded away into this cool reservoir. You can actually go like canoeing up there. If you were to stand on the ground, here you are, you wouldn't even recognize that you were in an impact crater site, right? You can't really understand what's going on. It just looks like some forest with a cool circular river. There's some other pictures of people taking trips up there. Here you can almost, even from airplane height, you might not necessarily get it. Once you go to outer space, though, you think, okay, I see what's going on there. That's an impact crater site.
Has there
Okay.
been a crater that like made water fill in it? Like, you know how like you dig so deep underground and water
hit
just
water-
fills up?
Sure. I'm sure there has been. You know, another interesting question is, remember, Andrew, that 2/3 of the surface of Earth is covered in water? Another reason we don't notice a lot of impact craters on Earth is because 66% of the time, the impacts strike either in the oceans or in Antarctica. We believe that the impact site that knocked off the dinosaurs took place in the Yucatan Peninsula near Mexico, and it's called the Chicxulub crater. And the reason why it took people such a long time to find the Chicxulub crater is because the Chicxulub crater is like partially buried by jungle and partially buried by the Gulf of Mexico. You have to use radar imaging to find the rim underneath the ocean. So that's not a perfect answer to your question, Andrew, but it gets you thinking that, yeah, sometimes water does fill up these things. There was one that I remember happening in Peru. There was this BBC impact crater. Was it in Peru or somewhere in South America? Where now, sorry, where a bunch of people were killed because not only did it knock into the water table, but it like released a whole bunch of pockets of arsenic, and all these people that went to investigate it started getting sick and falling into the crater and dying. And they actually they thought at first that aliens had sent toxic poison to Earth or something. It was a totally wild thing. So let's see if I can find the name of this small village or wherever it was. Yeah. Here, Caracas. So let's see if I can do paste Caracas impact crater. So now that it took me a minute to think about it, Andrew, but here's a great example of this meteoroid rather. That, come on, my internet's freezing up on me here. Give me the picture. I don't know what's going on. Everything I click on. Oh, there we go. Wow. Okay, sorry, my internet just had a little freak out. So apparently, this thing didn't kill anyone directly, if you can see it, but a small meteoroid struck the Earth. It blasted open the water table, and the water table contained pockets of some naturally forming arsenic gas. So all the people in the town came over to think, whoa, what the hell just happened? They started breathing in the arsenic and falling over the edge and dying. And then people came to see what are the people who are dying doing, and then they started dying, and it created this like little health emergency. And eventually the scientists figured out, hey, don't go near that thing for a little while. It's releasing arsenic gas. So in a way, this kind of indirectly killed people. There's never been a recorded instance of, I believe, people directly dying from meteor impact, although I do have a couple of funny pictures. And by funny, I mean funny in quotes. Let's see if it's here. Let me see if I can show you guys this slideshow. This is pretty great. share screen. Here we go. So this guy definitely had a bad day. This is somewhere in Australia. The back of someone's car was struck by a meteor. Look at that, just tore right through the trunk of his car there. Although these meteorite samples are actually, they're quite valuable. So you know, he probably got to sell this thing for several $1,000s or tens of thousands of dollars. He might have made his money back on that one. It's hard to say. Okay, so what's the big planetary geology picture about this? Before I go any further, before I give you some notes, I want to show you guys 3 pictures from my lecture on the Earth here. So let me escape the, oh, I had the damn picture right here the whole time. I want to show you pictures of 3 different planetary surfaces and see if you can guess what they are, okay? So I'm going to show you 3 different terrestrial planet surfaces. There's no reason you'll know the answers, but you're going to guess. That's part of the fun of the game. Take a guess what planetary surface you're looking at.
Jupiter.
No, I'm only talking terrestrial planets. Jupiter is a gas giant, Jake.
Oh,
Jupiter doesn't have a surface, right, Jake?
correct. That's correct.
Okay.
Mars.
This is not Mars. You had a 1 in 4 chance of guessing correctly. Now you have a 1 in 3 chance of guessing, or 1 in 5 of guessing correctly, I guess.
Venus.
This is Venus. How about this planet?
Kind of looks like Earth.
It kind of looks a hell of a lot like Earth because it is Earth. Because you can, and what do you see? What's the
I could see Africa and South America and America. Right. I think Australia.
This is why even if you look at a grayscale image of Earth, you know it's Earth because you see these continents. And what form of planetary geology do continents get caused by? Continents are an example of what type of planetary geology?
Plate tectonics.
Very good. You know, Earth is the only planet that has a full, robust set of plate tectonics. And that's why Earth's continents are so prominent. Look at Venus. Do you notice that there are no big continents on Venus? I mean, there might be this little hill here, but there's no major continents like that. This suggests that Venus does not have an active set of plate tectonics. That's a planetary mystery I need to explain to you. Okay, what are we looking at here?
Mars.
Yeah, and you're going to look at this a lot during today's lab. Now listen, Mars is kind of an interesting schizophrenic planet. It's got some cool evidence of past active geology in its northern hemisphere. It's got giant canyons like the Valles Marineris. It has these massive volcanoes like Olympus Mons. But when you go to the southern hemisphere, it looks as chewed up and as cratered as the moon or Mercury. So it's got like a dead layer or a dead zone. And then it's got a zone that maybe is not alive, but this used to be happening up here. There used to be some cool geology. Over time, though, you can see the craters are starting to creep in the northern hemisphere as well. And this kind of brings us around to my point. Like if you compared Earth and the moon, I got a couple of demos here. Here's the moon, and here's Earth. Relative to outer space, Earth and the moon kind of sit next to each other. The Earth is way bigger than the moon, but which of these 2 objects shows evidence of impact cratering?
Well, both do.
But not on the same scale, right?
The moon has
more.
Right, Jake. So you wouldn't imagine, for instance, that all the craters just happen to miss the Earth and just hit the moon instead, right? We don't see more craters on the moon because they only hit the moon in greater numbers than they hit the Earth. That wouldn't make any sense, right? Why do I see more craters on the moon than I do on Earth, Jake?
Well, the moon is not like technically dead, but I mean like you said, there's 2/3 of Earth is covered in water, so you can't see.
Forget about the water, though. The water is, that's almost a distraction. I would expect to see the continents covered with cratering. If 1/3 is continents, I should see, it's not like only 2/3 of the moon is covered in craters. Every fucking square inch on the moon is covered with craters, a variety. I mean, do I need to show you the moon again so you can remember what this thing looks like? Like the surface of the moon ain't just like hit 1 or 2 or 3 times. The surface of the moon, there isn't a bloody centimeter on this thing that isn't covered. Look, slide 30. This is what the moon looks like. 39. Do the continents of Earth look like that?
No.
No. Why not? Why are there more impacts on the moon than there are on Earth? No?
I don't know. I can't guess.
Would it have to do anything with the atmosphere?
Enrique, the atmosphere will block small meteoroids, but it'll only block them up to about 1 kilometer. Sorry, not even 1 kilometer. Only 1 meter in diameter. So, Enrique, if your meteoroid that's striking, hold on, how do I get out of this? Sorry. If your rock is about this big, then yeah, the atmosphere will burn it up into dust. But the atmosphere only protects us from little guys like this. It doesn't protect us from the big boys. And if you have a question like, well, how often does Earth get hit? Well, that question doesn't necessarily make sense. You have to ask, how often does Earth get hit with size X meteoroid? And the answer to that is here. Function F5-109. So to answer that question, every hour of every day, Earth is struck by a 1 meter size object, which, as Enrique suggested, will burn up in our atmosphere. But every year, we can expect to get struck by something of order 10 meters, which will make a small crater or an atmospheric explosion, like that one that we saw in Peru. Every 1,000 years, you might get struck by something 100 meters. That could almost make a big crater. Every couple 100 million years, you might get struck with a meteor crater-sized 5 kilometer object. And maybe once in 1 billion years to once in Earth's history, you get struck with the big boy, the dinosaur-killing sized meteoroids, the ones that create widespread climate change and change the number of species that exist on Earth. So the atmosphere will protect you in this small range, Enrique, but time is long, and we've been certainly hit with a whole bunch of these. Why does the moon look so cratered, and does Earth look so smooth?
Because there's no erosion in the moon?
That's right. On Earth, other forms of geology erase the craters. Now you're catching on. Let's take this as a note because we've just learned something important. Nicely done, Matt. Okay. Let's talk about some rules for impact craters. The first piece of business goes like this. All planets get hit with, I can call them impactors, but I'm going to call them meteoroids instead. And to say this quite literally, the size of a planet doesn't matter. That's because there is such an abundance of time and such an abundance of meteoroids that I would argue to you, Matt, I would argue to you, where am I here? That if there is a place on the moon that looks like this, that every patch of Earth has been hit with just as many craters. The ground under your feet has been hit with just as many craters over the last 4.6 billion years. Earth was hit just as many times, and I'm sure it killed a few caribou and bunnies and reindeers or woolly mammoths or what, all right? However, it's clearly obvious that not all planets show evidence of impact cratering. They don't show the scars. And if we ask the question why, the answer is other forms of geology erase craters. Yes, erosion can erase craters, but you will see on Mars today that so can volcanism and even tectonics. This leads us to a very important conclusion that is one of the key bases of planetary science, which says something like this. The number of impact craters, or let's not say the number, let's say the density of impact craters. The density of impact craters on a surface is a measure, the surface age of a planet, not the age of the planet, but the surface age. So in other words, if you have a high density of craters, that means you have an old planetary surface. If you have a low density of craters or no craters, that is a young planetary surface. I think I should have changed my exclamation point there. In fact, there's something that I need you guys to think about before we take our break here. A moment ago, I showed you the relative frequency with which craters of various sizes strike Earth. I showed you this graph. And you can see that getting struck by sort of large impactors of this size only happen in the 100 million years to billion year range. But you would be wrong to conclude that it was always so. That's because when our solar system first formed, it was a dirty, messy, and violent place that had many more meteoroids than we see today. The early solar system, remember, looked something like a big dusty disk of gas, something we call the protosolar nebula. And the protosolar nebula didn't have a few meteoroids floating around space. It had probably millions of small, medium, and large size objects whipping around the sun in a kind of giant king of the mountain crash 'em up that formed the planets. In the early solar system, there must have been a lot more rocky and metallic debris floating around, zinging into the surfaces of the planets. And the concept we have for this is something called the heavy bombardment period. I had a couple of pictures of that, or I tried to have one earlier. Yeah. The idea was that in the early solar system, Earth, Venus, Mercury, Mars, all the planets would have been getting pelted, not just by your small garden variety asteroid, but by some kind of big whoppers that even exceeded the size of a small moon. And these would have left violent collisions that greatly distorted the surfaces of the planets. One of the reasons we know that such a period exists is because we did radioactive dating on the surface of the moon. And the moon, as you know, has two surfaces. Let's look at lunar Maria for a second. When the Apollo astronauts landed on the moon, they took geological rock samples and used radioactivity to date the lunar Maria compared to the craters of the moon. And let's look at this picture here for a second. Let's apply the logic that we just learned. We know that the density of craters implies the age of a surface, right? So which surface should be younger? The Maria, this is a Maria, or the highlands over here? These are the highlands. Which surface should be a younger surface?
The Maria.
Right. The Maria are smooth and show few craters. The highlands show lots of craters. Now, it would be one thing if we radioactive dated the Maria and it turned out that they formed 1,000 years ago, and then we dated the highlands and they formed 4 billion years ago. But instead, we got very different results. The age of the lunar Maria turned out to be 3.9 billion years old. The highlands turned out to be 4.6 billion years old. And the reason why that's troubling is, okay, I can understand the highlands being as old as the solar system because they were around from the beginning. The moon has no other types of geology, so the moon just got hit a bunch by these giant meteoroids. But how is it that this thing went smooth basically 4 billion years ago, and it hasn't gotten that much more cratering since then, right? You would think that if this all happened in 1 billion years, then in 4 billion years, you'd expect this to look even worse. The conclusion they drew was that in the first billion years of the solar system, things were much, much more violent. And thus we came up with the concept of what is known as the heavy bombardment period, which is defined here as a period 4.1 to 3.8 billion years ago. Okay, during this time, a disproportionately large number of asteroids collided with the early terrestrial planets in the early solar system, and they created all of the crazy cratering that we see on the surface of the moon. So for instance, a lot of scientists will do this. They'll look at the surface of the planet Mercury, and if you look at the surface of the planet Mercury here, you'll notice that like the moon, I wonder if we have a close-up of this. Like the moon, it is just covered everywhere with impact crater after impact crater. Scientists will say, you know what? A lot of that is heavy bombardment. That's evidence of just a crazy period of bombardment that struck those planets. Let's just take a quick note on that, and then we'll pause before our lab. I wanted to get to that because that's going to be instrumental in understanding our lab today. So heavy bombardment period was a period that went from 4.6 billion years to 3.8 billion years ago, when frequent large, we could call them meteoroids, but sometimes they're so big. They notice that the Wikipedia called them asteroids. People often call them planetesimals. An early asteroid would be a planetesimal because these were things that formed the planets. Frequent large meteoroids and planetesimals struck the surfaces of the terrestrial planets. The other idea is that this formed the cratered, we call them highlands. And we see these cratered highlands on, obviously, the moon. We see them on Mercury. And as you'll discover in today's lab, we even see them on Mars. Mars shows a little bit of heavy bombardment as well. We do not see them on Venus and Earth. Venus and Earth cleaned up their heavy bombardment. No on Earth, no on Venus. All right. What do you guys think about taking a little?
I can't see the rest of the board.
Okay. You guys want to take a safety break?
Yes,
Stay awake
please.
for safety's sake. It's 5 of. We'll go until about 1:15. Then we'll start our lab. Everyone down with that? Okay. Ava, as I mentioned at the beginning of class, we are doing lab 10. And the lab that we are doing is the ages of Martian landscapes. And for this one, I'm going to be using this map, and I'm actually going to be writing my answers right onto the worksheet online. I'm not even going to print mine out today. That's because I don't want to use my phone because I'm going to have to go back and forth between the screen and here. So you might actually want to just use your Acrobat reader. Okay, I'll see you guys in 20 minutes. Take a break. Okay, friends, sorry about the delay. We're back. It's time for us to do lab number 10, relative ages of Martian landscapes. This is going to work a little differently than some of our other labs. What's going to happen is we're going to attempt to kind of do this thing sort of on the computer, or at least I am, and you guys can even submit it that way. I am going to need a few pictures. So in order to keep the internet from grinding to a halt, I need to, we'll keep Wolf Creek and Meteor Crater open just in case. Don't think I'll need any of this. Let's get rid of that. I have this opened up in Acrobat so that I can write things onto it. So I can delete that there. I am going to want to make use of this Mars MOLA map, but I think I'd like to open it up once again using Acrobat. I think that'll go a little bit better. Labs. Mars topographical map. Yeah, cool. All right, so now I can kind of switch back and forth there. That's pretty nice. So I can get rid of this. Okay, you guys ready to go on your end? Do you have it all figured out what you're going to do?
Should we print out the map as well?
Well, mostly you're going to be watching me do it, right? So that's a reason why not. Another reason is you can obviously open it up on your computer just like I did. I'd imagine that would suck up a lot of red and orange and blue ink, and that might not be a great thing. Oh, you actually printed the map. I actually have a hard copy of it here in my drawer, but the problem is to show it to you, I'll have to use that phone app, and then it'll be hard for me to show you other pictures I want to show you. So what we're going to do is just like last week where we had a glorified excuse to sort of explore the surface of the moon, this is a glorified excuse to explore the surface of Mars. And what we're going to do is we're going to just kind of go through this thing here, and we're going to answer some basic questions about Mars together. We'll write the answers together in a way that we understand the point. So don't forget to put your name at the top, and don't forget to write lab 10. And then if you can also put your section AS1010, 001, 002, or 101. You guys can see all that when I type, right? Can you see that red stuff?
Yep.
Okay, good. All right, so the Mars MOLA map was made by an orbiting satellite that flies around Mars and shines a laser at the surface. Am I recording? Yes, I am recording. And as it bounces off the surface, it gets information about elevation on the planet. So let's just take a look at the map and orient ourselves here. There's a color key that tells us how to understand the elevations. Where's that color key? There it is. Where can I put you guys so that I won't be irritated? Let's put you over here. So what are the colors that represent the highest elevations, and what colors represent the lowest elevations according to this legend here?
Like the deep blues and purples are the lower elevations,
And then the higher elevations?
are like almost monochromatic, like white, gray.
Light gray. So let's like poke around. Where do we see those highest elevations? This will take longer and longer and longer the less you guys participate. I will just wait for one of you to answer. So by participating sooner, we'll get done with this faster. Keep that in mind as we go forward. Where do we see where do we see the highest elevations on the map?
Like the mountain ranges.
Tops of the these are volcanoes actually.
Oh, okay.
Tops of volcanoes. Notice that the planetias and things in the lower northern hemisphere, we see lower elevations. Okay.
What are those dots? What are those circles? Those bubbles all over the thing, all over this map.
Oh, these are impact craters, just like we learned about. That's all impact cratering.
I thought that one is that one, that big one right there.
But also the small ones are too. Remember, planets get hit by a variety of different sizes of impactors. There are small impact craters and there are larger ones, all the way up to the Aguirre Planitia, right? The only other thing I have to tell you is there are some longitudes and latitudes that we're going to want to pay attention to here. Mars has two longitude systems, a red base western longitude and a black eastern longitude. We're going to use the red base western longitudes today. Okay. Let's just get into it since I'm already running behind a little bit. Question 1 isn't really a question, but question 2 is. It says, you've probably noticed that the northern hemisphere of Mars is very volcanic and the southern hemisphere is heavily cratered. Based on the concept of crater density, which hemisphere do you think shows the oldest landscape, northern or southern? What would you guys say is the older landscape, the southern hemisphere or the northern hemisphere? Whoop.
The northern, because there's less craters.
Wait a minute, it asked for the oldest surface. I thought we learned that the older, that doesn't make sense, Andrew. Should an old surface show more craters or less craters?
It would be the southern, since it is heavily cratered.
That's right, Frank. Remember, Andrew, that if you're old, that means you've been sitting around since the heavy bombardment period, getting pegged by all of these impact craters, right? This is all heavy bombardment.
Yeah.
Up here is smooth, suggesting some, I mean, Andrew, you don't believe that all the craters just happened to hit the southern hemisphere and they just missed the northern hemisphere. The reason why the northern hemisphere is smooth isn't because heavy bombardment missed me. It's that this must have been cratered just as many times as the lower places. But some other type of geology came along to erase the craters. So the southern hemisphere is the oldest. Okay. Inspect the Mars globe or map provided in class. Locate two basins in the southern hemisphere. Aguirre Planitia is near longitude 40 degrees, and Hellas Planitia is near longitude 290 degrees. These two basins were probably formed by giant impacts of meteoroids. The smooth surfaces at the bottom of these large craters are lava flows. Use the map and try to determine if you think these lava flows occurred before or after most of the heavy bombardment in the early solar system. Use crater density around the outside of the two craters and compare it to the density of craters inside. So the question they're asking is, did the lava flows occur before or after heavy bombardment? So here's the Hellas Planitia and there's the Aguirre Planitia. What do you think, class? Did the lava flows in here occur before or after the heavy bombardment?
Would it be after the heavy bombardment?
Correct. And what's the evidence why? Why means, unlike our president and Rudy Giuliani, we need to back up our extraordinary claims with observational evidence, things that everyone can go and examine, right? So if we're going to say that the lava flows occurred after heavy bombardment, what is our evidence here that explains why? How do you know that this occurred after the heavy bombardment? Frank. Psst. When in doubt, use crater density.
Well, with the heavy bombardment, it probably shifted the plates, which could have caused the volcanoes to erupt.
No.
Oh.
Volcanism is caused by internal heat. Impact craters, unless they are extraordinary. Well, okay. Yes, in this case, these massive impactors could have made cracks in the lithosphere that would allow lava to come up. In that sense, you are correct, Frank. But
okay,
you need observational evidence. Say, I see this on the surface that tells me this is younger than the other one. Remember, a planetary scientist used crater density. So how can you argue that this is younger than this based on crater density? So I'm looking for a very simple answer here. In other words, Frank, how do you know this is young and how do you know that's old? How did you know that? How did you know the answer that you got?
Because of the amount of craters it had.
The amount of craters that what had? Flush out your answer more. You're still being vague. What has more craters? What has less craters? Say it explicitly.
The opposite side of the Hellas Planitia over where.
Here, you need some vocabulary terms, okay? This area are called the highlands. This area is called the basin. So this is the basin, okay? And over there, the highlands. So what do you want to say about craters in the basin versus craters in the highlands?
In the it's like in the highlands there were. It's like most of the craters were over here, and in the basin it looked like it was almost untouched.
It's smoother. There are more craters on the highlands. The density of craters are higher on the highlands than the density of craters in the basin. That's all I wanted you to say. All right?
Okay.
So for Y, let's say the density of craters. Oh, looks like I've done this before. The density of craters in the basins is much lower than the surrounding highlands. That's creepy. Okay, at first this seems to be
much lower than
the surrounding highlands.
I found it.
Let me know when you're done.
I'm done.
All right. Now, guys, at first this looks obvious. Heavy bombardment is here and it's smoother over there. But I have to ask you guys, how do you feel about the size of these impactors? Are these a sort of garden variety impactor, or are these sort of extraordinarily sized impactors? How big are these things anyways? Let's see if we can take them down and use our, I'm going to teach you guys a little bit about maps here, okay? Do you see down here we have something called Mercator projections. Remember that this is a flattened map from a spherical globe. So unlike a map of Rhode Island where 1 inch might equal 10 miles, here, how many inches or how many millimeters equals how many kilometers will depend upon what latitude you're at. Let's see if we can figure out the latitude of these guys. This Hellas Planitia here is maybe 1, 2 big ticks, 2.5 big ticks down. Let's see what that is. -30, -50, -35, -40, maybe 40. Yeah, -40. Okay. So let's measure the size of the Hellas Planitia. Then let's put it over the Mercator projection of that same size. So here, oops, start here. That's about the size of this beast. And now let's select it. Watch this tricky Ricky maneuver. Let's move it down to there. Roughly, according to this, how many kilometers across is the Hellas Planitia?
About 1,500.
No, look, you have to learn how to read this Mercator projection. The Mercator projection is 2,000 kilometers, but that line bends depending on what latitude you're at.
Oh.
So try again. Anything that touches this black line, Jake, is 2,000 kilometers. Our line,
Okay.
Our line is at -40 latitude, and it goes all the way out to here. So
2,100.
yeah, 2,200 kilometers. Let's say the impactor that created this is 1/10 to 100th the diameter. If this is 2,200 kilometers across, how big might the impactor have been? Don't think too hard, guys. Do you understand? Like, how big would the thing, how big do you think the asteroid that caused that hole is?
Big.
That's wishy-washy talk. You want to be quantitative. I'm trying to figure out how often those things might have happened. An impactor is roughly 1/10 the diameter of the crater. The crater is 2,200 kilometers. Can anyone in my class divide 2,200 by 10? I don't want to tax you guys too hard here. I don't want to like break your minds on a Monday morning, but I was just hoping you could do 2,200 divided by 10.
220.
220.
Okay, so how often would something that was 200 kilometers be expected to strike Mars?
I mean, almost never.
Once in a billion years, maybe. So I guess my point that I'm trying to make, Jake, is if those extraordinarily large impactors are striking infrequently, why did both of them happen after heavy bombardment? Why didn't one of them happen in the middle of heavy bombardment or at the beginning? Isn't that kind of wild?
Yeah.
You've got all this cratering, little crater, splat, 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 and then it's all about to be over. And then just at the end, bada boom, the big guys come. That's kind of weird. I would expect these not to have happened at the same time. Let's read the question, okay? Use the Mars map to inspect the rim of Aegirre Planitia and Hellas Planitia. Look to see if the rims have more craters than the lava flows inside the rim. Look for evidence of ghost craters, which have been filled with lava. Based on the appearance of the rims, which historical account seems more likely to you? The giant impacts occurred early when most of the other impacts occurred and excavated the large basins with their surrounding rims. The lava filled the basins later after the cratering activity of the heavy bombardment. Or B, the giant impacts just happened to occur very late after most of the other craters had formed, and the lava filled the basins immediately. So based on what the rims look like, do we think that these craters happened at the end or sometime during heavy bombardment?
I think it'd be during,
Yeah, and what would be your evidence?
because it looks like there's like a lot of cratering around the rims of these, so it looks like they formed in the middle of it.
Right. You can kind of tell a lot about a crater by the rim. The rim tells you how old it is. Like, for instance, Jake, while we're talking here, suppose I asked you to compare two craters. Compare Huygens to crater Dawes. Can you tell me by looking which one is younger?
Does.
Yeah, and how do you know that Dawes is younger?
It's almost completely smooth inside, and it has a very like prolific rim.
Yeah, the rim is really crispy. How does the Huygens rim look by comparison?
Like it's been eroded almost.
It's probably erosion is worn away at this thing, plus a little bit of cratering too. It's been beat to shit over the years. This guy is still intact. Now let's take that knowledge with us and let's go down here. Notice that the rims are quite beat up and eroded, right? Especially in the Aguirre planitia. So I guess we could say, let's see if we can circle our answer here. Oops. A. The impacts occurred early. And for the evidence, it sounds like your idea was the basin, the rims of the crater is what I want to say. Oh, shoot. The rims of the planitia show a higher density of cratering or erosion than the basins. So the basins must have been older than the rims, than the impactor itself.
Oh wait.
Let me know when you're done, buddy.
I'm all set.
All right.
Thank you.
Look carefully at the crater density along the rim of Hellas and Aguirre. The basin that is older should have more craters on top of its rim than the younger one. Does the Hellas or Aguirre basin look older? What do you guys think based on this image here? Should Hellas
Aguirre.
be? Yeah, Aguirre looks a little bit older to me. Aguirre. And for why, the basin, the crater density on crater density erosion of Aguirre's rim seems greater than that of Hellas. Oh, wow. Sorry. I'm just gonna grab my water. Hold on. Okay, can we move on?
Yep.
Cool beans. Here we go. Most of the volcanoes on Mars look like mountains with a crater on their tops. Okay, I didn't quite get to talk about this in class today, but the term for the opening at the top of a volcano, it's not called a crater, but it's called a caldera, okay? So the opening at the top of a volcano, here's a new vocabulary, caldera. I wanted to get to volcanoes today, but I ran out of time. So we should say most of the volcanoes on Mars look like mountains with a caldera on their tops. These are not impact craters, but are instead calderas. Use the map to estimate how many volcanoes you can identify on Mars. Holy crap. Okay, let's count them together because this can be kind of a big job here. How many volcanoes can we find? Now, from now on, anything, the names of the volcanoes on Mars have a couple of different names. Anything that is a mons will be a volcano. Anything that is a tholus will be a volcano. Anything that is a patera will be a volcano. So let's see. I spy with my little eye. 1, 2, 3, 4 big ones. 5, 6, 7, 8. Oops. 9, 10, 11, 12. He's got 12 up there. Keep looking around with me, guys, because I could miss one. So I see 12. Don't see too much down here. There's some over on the right-hand side, too. There we go. 13, 14, 15, 16,
17.
17. I think there's some at the South Pole too, which is kind of cool. We're at 17. Let's look up here. 18, 19. There's got to be at least one more. Okay, 20. It's close to 20. Let's do tilde 20. Tilde, of course. Oh, I can't do tilde. They don't let me do tilde. Okay, fine. About 20. Okay. It says list the names of as many as possible. We're just going to list the names of the 4 biggest volcanoes. They are, the 4 big boys are the ones that we find over here in the Tharsis Montes range. Olympus Mons, Ascraeus Mons, Pavonis Mons, and Arcea Mons. I'll show you how to spell those. Olympus Mons. Oh, okay, these have them. There we go. Olympus Mons, Arcea Mons, Pavonis Mons, and Ascraeus Mons are the tallest 4 volcanoes on Mars. We're making good time here. We cool?
Yep.
Using the color codes, which volcanic feature has the highest elevation or the tallest? Do you guys know which one that is?
Olympus Mons.
That's right. It's the tallest volcano in the damn solar system.
Oh, I don't have the question written down for 8 or 9.
Just write this instead. Write question 8, tallest volcano, question mark. That's 2 words.
Tallest volcano?
Yeah. And don't worry about
All
writing
right.
the question for 9. Just write the answer for 9, okay? I'll know what it is.
All right.
Save you some time, Andrew. Okay, this next question is actually quite complex. It took me a few go-throughs to understand what they were getting at. I didn't understand it at first. If you were to count craters on or near these volcanoes, would you be able to infer the age of the volcanoes relative to the surrounding plains? Now, the first time I looked at this, I got confused because I said, well, the plains around the volcanoes are relatively crater-free, and the volcanoes are relatively crater-free. So no craters here, no craters there. How am I supposed to compare the volcano to the surrounding plains? And then I realized the volcanoes and the plains aren't quite as crater-free as I originally noticed. As you zoom in, you see a few more. Let's look at a photograph. This is an excuse to look at a photograph of Olympus Mons together. Sometimes you really have to look at a high-resolution photograph to understand what the question means. This is, I think, for Voyager 1, it's a famous image of Olympus Mons, pretty high resolution. Look at that. That's the top of this massive volcano. This thing is huge. It's like, I think Mount Everest is 9 kilometers tall. Olympus Mons is 27 kilometers tall. This is 3 times taller than Mount Everest. What do you think about what's going on here? What conclusions can you draw by looking at the top of this volcano?
It's got a good amount of cratering.
Cratering, all calderaing. Which are the craters and which are the calderas? Let's play a game called Crater or Caldera. Let's start with the main opening. Crater or caldera?
I mean, I would assume caldera.
Good. How about this one? Crater or
Crater.
caldera? How about this one?
Caldera.
Good. How about this one?
Crater.
Good. How about this one?
Crater.
Can you kind of see the difference now between the craters and the
I could see the difference. Those are deeper and that one's
kind of got a
like
crispier
more
rim.
up.
Yeah, these have these like shallow rims, probably because they collapsed a magma chamber underneath them. What do you think it means if the tallest volcano on Mars has not 1, but 2 craters at their very tops? I mean, if any craters were going to get paved over, you'd expect them to be right near the top of the volcano, right? What does it mean that I see 2 craters at the top of the volcano?
It's young. It's pretty young.
It's young compared to the highlands, but did this thing erupt yesterday? Did it erupt last year?
No, it's been dormant.
Yeah, dormant enough where a couple of craters could hit the surface. What if I told you, Jake, that this one was about 10 kilometers across and this one's about 15 kilometers across? How big would the impactors have to have been that created those craters?
Tiny. I mean, like
No. There's a rule. What's the rule? It's 1/10 of the
divide
diameter.
by 10.
Divide by 10. So how big were those objects?
1 kilometer,
To 2
1.5.
Yeah. Okay. And how often would I expect them to hit Mars today?
Every million years.
Somewhere between 1 million and even 100 million even, right? So how many years has it been since that volcano erupted?
$200 million years, maybe.
Okay. And now, to test your skill, let's go back to Olympus Mons and see when the last eruption was. Hold on. Look at this. Crater counts from the lava flows say the northwestern flank ranges from anywhere from 115 million years old to only 2 million years old. So you were okay. Crater size on the caldera floors range from 350 to 150 million years. So you didn't do so bad, did you? Just by counting those two craters. You were in the ballpark, kind of, loosely speaking. So what's the answer to this question? If you were to count craters, would you be able to infer the age of the volcanoes relative to the surrounding plains?
Yes.
Yes. And that's because even 1 or 2 impact craters is enough to estimate the age of the surface of the volcano. Andrew, let me know when I can move forward.
All right. Oh, I
Now-
didn't even get 10 either.
Just don't worry about writing the question. Just write the answers, okay, Andrew? I'll give you a pass.
All right.
Okay, now it's time for us to talk about Mars's version of the Grand Canyon. Not only does Mars have supersized volcanoes, Mars also has a supersized Grand Canyon. It's 14 times longer than our Grand Canyon and 7 times deeper, okay? It's known as the Valles Marineris, after the Mariner spacecraft which first charted its surface. Pictures of this thing are truly astounding. Let's see if we can find, there's one on the wiki, or there's one somewhere that's, by the way, the Valles Marineris is so big, it almost covers like a third of the surface of Mars as seen from space. Look at that stupid thing. This is a picture in true color. It can be a little difficult to see what's going on. This one has sort of highlighted topography differences. Would you guys say the Valles Marineris is a young geological feature or an old geological feature? Let's see if we can zoom in there.
I would say young, on the younger side.
Yeah, what tells you that, Jake? Sorry, I'm looking for one that I can.
The rim looks pretty like crisp and like relatively crater.
Especially in the valley. Okay, that's why this is taking so long. Sorry, there's a lag here. This is a super, super high resolution image, so this is going to look totally awesome. Notice as it comes into view here that the northern plains are covered in impact craters. But when you look at the basin of the channel itself, it's almost completely blemish-free in terms of craters. It's not blemish-free, but it's completely crater-free, I should say. Sorry, this is, I think this is like a 9,000 pixel image, so. While that's loading, let's read the question. Inspect the area, south of the Valles Marineris between longitudes 45 and 100 degrees. Notice the area is not uniformly cratered or wrinkled. A boundary seems to occur at what longitude? So they're basically asking about this region here, south of the canyon. Let me change to red because I think it has slightly better contrast ratio. They're asking us to compare this area here, south of the canyon in that range. Do you guys see a geological boundary forming somewhere?
Yeah.
Where? What is the boundary? A vertical boundary.
Nectaris fossae.
Sorry, guys. Very good. Now we're supposed to estimate what its longitude is. So the longitude, if we go from here.
I can't see your computer screen for some reason.
Can anyone else?
I can see it.
I can see it.
Huh. You don't see anything, Andrew?
No, I don't see anything.
Do you see that?
No, I don't see anything.
Well, it took me. What do you see, Andrew? Let's start there. I mean,
I only see your face. That's the only thing I see. I don't see what's on the other screen.
so wacky. All right, let me stop share and reshare. See if that helps. How about now?
Yes, now I see it.
All right. Well, whatever that was, we dealt with it. Guys, let's see if we can figure out the longitude of the Nectaris fossae. It seems to go to like that tick mark there. So let's kind of, wait, let's make sure I can make that really vertical. All right. Fuck. Okay. Now let's try to scroll up. What would you say that longitude is? Oops. So that's 30 and that's 60 and we're about there. I think the big ticks are 5 and the little ticks are 1 degree.
58.
Yeah. Can I get a little degree symbol here? How do you get a degree symbol? Watch this. That, ready? Copy. Who's tricky? I'm tricky.
Wow.
Okay. Nice, right? 58 degrees. Is the younger surface to the east or the west of this boundary?
East, I think.
Wait, east is yellow, west is red. Which is the younger surface?
Oh, then west.
West is the younger surface, right? Okay. Look at the smooth plain named Tharsis Montes. Does the crater density suggest that Tharsis Montes is older, younger, or the same age as the region south of Valles Marineris? Now they want us to compare this zone south of the canyon to this area up here near the volcanoes. Is the area near the volcanoes older, younger, or the same age as the area south of the canyon?
It looks slightly younger.
Yeah, there's a few more craters in this red area than there are craters in this red area over here, right? So what you're seeing, Jake, is the closer and closer you get to the volcanoes, the younger the surface gets. Why is that? Because the volcanic eruptions are repaving
Lava
over
flow.
the surface. Yeah, these are all lava flows. You can see different epochs. Probably at one point there was some yellow lava flow, then some red lava flow, then some really red, then even the brown stuff sits on top of the red. You can see the epochs of lava flows getting smaller and smaller as they go forward. That's as Mars cools, each epoch of lava eruption is getting wimpier and wimpier. So that's younger is the answer to that question. Along the rim, the north rim of Valles Marineris is a place called Candor Chasma Rim. Does this area suggest that the canyon is older or younger than the plains to the north and the south? Now the Candor Chasma Rim is this area up here. Does that look older or younger than the plains? Ooh, wow, that's like a little too much detail. Let's get back out again. 9,000 pixels is kind of hard to do over the internet. Does the area inside this canyon look, what did you decide, Jake? The area inside the canyon was older or younger than the plains to the north and the south?
Younger.
Yeah, because you see craters north and south, but you don't see them inside the rim. Look at the rims of Valles Marineris. Is there anything along the north and south rim that shows evidence of water flowing on Mars? What do you guys think? Do you see any evidence of water flows here?
Yes.
Yeah. Honestly, like, okay, hold on. This isn't going so well.
Especially like to the left.
Yeah, you know what I was thinking too? You know what this stuff in here reminds me of? Let's see if we can zoom in on this. This might freak out on me. Don't these kind of look like sand dunes, like the kind of sand dunes that you see along the beach where there's lots of water erosion?
Mm-hmm.
Look at all that like serpentines. It looks like water flowed all
Leaning.
throughout. Yeah, so hell yeah. Yes. Look at the crater inside the Valles Marineris and let's choose one of the following historical accounts. The canyon forms before the plains and lava flows which made the plains did not reach the canyon. The canyon was cut into the rock by a river of lava. The canyon forms a boundary between two plains of different ages, or the plains formed first and at one time covered the area. Valles Marineris forms later from an unknown cause. None of these options are awesome, but which is the least sucky option?
I would say B or C.
Well, let's talk about B. Like, lava doesn't cut rock. Lava paves things over, right? Lava doesn't carve out channels like water does. Lava builds things up. So you can't cut a channel with a river of lava. B is no good.
True.
As for the canyon forming a boundary between plains of different ages, you can clearly see that there's red stuff here and red stuff there that was once connected. Honestly, guys, I think the best answer is D. Those plains were there at one time, and then the canyon kind of ripped through them, and that's why it's so young. Okay, back to the action. Look at the area around the volcano Arsia Mons. Now, Arsia Mons is the volcano that's down here. It has a little ridge in it, okay? Using a magnified image, locate several ridges or channels on the side of Arsia Mons. Make sure the channels were made by the volcano. Follow the structures to see if they extend out into the surrounding plains. Look carefully for any evidence that Arsia Mons has been covered by another geological development. From this, choose one of the historical accounts. The volcano forms first and was later buried by a lava flow from another volcano. Or B, the volcano formed the plains from its own lava flow. Thus, the plains and the volcano have the same age. In order to understand what they're doing there, you need to see a high-resolution image of Arsia Mons. And there's a beautiful black and white one that's worth looking at here. Look at that channel there. Look at this volcano. First of all, look how smooth it is inside the basin. You see a few tiny little craters in there. Look at all these channels that suffered tons of tectonic stress as the volcano erupted. What is this stuff? What is this crap going on right there? Can you tell me what all that stuff is?
Is it Caldana? What that word?
Yeah. Very good. This is volcanic in nature. You know what these are, Jake? These are side vents when a volcano just blows a magma chamber out the side. And afterwards, what happens is the weight of the magma sitting on top of the empty chamber collapses the chamber. And these are structures called collapsed lava tubes. Based on the fact that you see these collapsed lava tubes, which answer here do you think makes the most sense? A or B?
B.
Yeah. Definitely those collapsed lava tubes were formed by the volcano itself. And so the volcano is forming the plains as well as the structure of the volcano. For our answer, just write collapsed lava tubes. That's the only answer you need. Okay, guys, I'm going to nix 17 and 18, just because I think we've done our share here today to explore the surface of Mars. So thank you for playing Mars topography with me.
14. Did we have an answer for 14?
Did I miss one?
Yeah, I'm missing 13 and 14.
I have 13, 14.
I have 13 and 14 too. Look,
Younger,
no
yes. I
12
think I
that was-
put that for 11 and 12.
but it was the same answer.
Oh, wait a minute. I think, oh, maybe I missed it.
Well, apparently there was no 12. So
Yeah, I caught.
Oh, okay.
So I just kind of like went over that.
are we clear?
Would you mind showing number 5 again? I was in the midst of writing it down and I didn't get it all.
That's fine. Cam, we can do 6 as well. 6 is about 20.
I'm all set, Professor.
All right. And Cam wanted number 2. Number 2 is Southern. Any other questions here?
Yeah, which ones at the end did you not do?
Oh, I just nixed off 17 and 18.
Okay, then what was 16?
The volcano forms the plains from its own lava flow. Thus, the plains and the volcano have the same age. Why do you think so? Because we see collapsed lava tubes.
Okay, thank you.
Sure. All right, everyone satisfied? Thank you for looking at the surface of Mars with me. I will see you guys on Wednesday. We will clean up geology, start atmospheres, and we'll do our homework on terrestrial geology. Sound like a plan? See you on Wednesday.